Hi everyone, Mr. Lee here. In this video, I'm going to go over objects moving along a banked curve. Now, what a banked curve is, it's a piece of surface that is at an angle, and objects go around and around on that angled surface. Now, a classic example here in the States, we have car races, and if you look at the tracks of those car races, we can see. So this is from the actual car's camera. We can see that the cars are at a very steep 31-degree incline. Okay, it's a very steep slope. This is what it would look like if you were to be in the driver's seat, and this is what it looks like from an aerial view. And this person over here, we can see by their foot and the way that they're leaning, it's a pretty steep slope. So that's what a banked curve is. All right, now for this this lecture, you have to use your imagination a little bit because what we're going to be doing is we're going to be working in like a 3D model, but we're trying to get that 3D model into a 2D point of view. Okay, so I'm going to go over different points of views so that we have a better picture overall. All right, let's begin. Now, let's do a quick review of centripetal motion because that will come into play. Now, if we were to take a look at the aerial view of this track, okay, we can imagine that this is just a giant circular track. This is aerial, and where you are on the track, so let's say the car is here, okay, the car will be moving forward, and we call that forward motion our our tangential velocity. So it doesn't matter where the car is along this track, this tangential velocity will always be tangent to the surface, or tangent to the curve of the circle. So I'm just drawing different parts around the track where the car could be. So just so you know, here, even though I'm pointing the velocity upwards, this car isn't being lifted off the ground. It's just moving what we call in a forward direction. And over here, even though I drew the tangential velocity downwards, it's not falling. It's just moving, around in a circle. And remember, this is an aerial view of the track. Another thing that you have to remember is that the centripetal acceleration will always point towards the middle of the circle, and this does come into play when we go for solving it. Now, another thing that you have to remember, if this is the center of the track, the centripetal acceleration always points towards the center of the track, and the radius r, okay, is from the center of the track to the object itself, and in this case, it'll be the car. All right. Now, let me show you my representation of this banked curve. I'm going to try my best to depict a 3D kind of thing using 2D drawings. All right, so this is like a slice of the, like a side profile of the track. So what I mean by that is the track actually continues, right, and it kind of curves out like this, right? And then we have like the middle of the road that kind of goes like this, okay, around that curve. All right, so whenever you see me draw this triangle, just know that we are on a banked curve, but it's like a slice of that curve. So the problems that you often face is if we have a car, right, and the car were to remain at a very specific point on the road. So let's say we have a car and that car is riding along the dotted line on the track. Okay, what is the very specific velocity the car needs to have in order to ride around that circle? Now, there is a very specific way I phrase that. And this is what we know, and we can go along use the conceptual and the formulas to really dive into why this happens. So according to our centripetal acceleration equation, vt squared divided by r, okay, and remember centripetal acceleration simply means that an object is moving around in a circle and it's accelerating towards the middle of the circle. It's constantly being pulled in, okay? If you have a very specific, okay, it's a very specific radius away, you must drive at a specific velocity, okay, in order to be moving around in that circle. So what this means for us for this banked curve is if v increases, our radius increases. And with my drawing over here, I'll show us why. If v decreases, our radius decreases. Okay, so let's go into what that means for us. Now remember, this is a side profile of this aerial view, and to be a little bit more specific, we are looking at the car when it's exactly right there. Okay, so I'm going to redraw this so I have a little bit more room to work with. There we go. So this is my triangle. Okay, the car is right there. That means the center of the track is somewhere over here. All right. Now, the center of the track is over here. That means that our centripetal acceleration is pointing to the left. Okay, keep that in mind. Now, what I mean by up here when we're talking about if our velocity increases, our radius increases, and if our velocity decreases, our radius decreases, this is what it means. So as you're going around and around in a curve, if our car slows down, the car will slide down the ramp. Okay, it'll eventually start to spiral in towards the bottom of the ramp. And so our radius decreases because if this is our original radius r away, okay, and this is still the center of the curve, if the car slides down the ramp, okay, because it is moving slower, we can see here that the radius r, it got smaller. Okay, but if the object sped up, I'm going to erase this. If the object speeds up, the car speeds up, that means it'll move up the ramp. Right? So if the object moves up the ramp, that means our radius r increases. So this is our r, and our r gets bigger. So the slower you are, the more towards the bottom of the curve you'll be, but the faster you are, the more up towards the top of the curve you'll be, okay, compared to the very, very middle. All right, so with that in mind, let's actually go into how we can set up our net force equation and how we can solve all of this. All right, now we're going to be drawing a lot of triangles, a lot of these bank curves through the course of this video, so we should get used to it. Right there, that's our theta. This is our angle. All right, if we have an object that's moving around in a bank curve, normally what we did for these inclined plane type of stuff, we adjusted our x and y axis. But I'm here to tell you, do not adjust your x and y axis. Our x and y axis has to remain what we conventionally know it as, where y is straight up and x is horizontal. And the reason for this is because of the direction of the centripetal acceleration. Now, I'm here to tell you that the centripetal acceleration is pointing towards the middle of the track. Okay, I'm just going to draw right there. That dot represents the middle of the track. So that means the centripetal acceleration is pointing along towards the middle. Now, the reason why we want to keep our x and y axis is because the acceleration is along this x axis. Okay. However, if we were to adjust the x and the y axis like so, this centripetal acceleration vector, it belongs in neither the x nor the y axis, and so our math gets really funky. Okay, so we don't want to adjust it, we want to keep it as upright. And the rest of the steps follows as what we are normally used to. I'm going to create my weight force first. So Fg going down, okay, and this Fg is along my y-axis, so I don't have to break it up into its components, all right, and then I have my normal force going straight up. All right, now notice here, my normal force, it belongs in neither my y nor my x, so I will have to break up my my f of n. All right, so those are my two forces. So for my free body diagram, that's what I would draw. And remember the tires, we have our back tires here, okay, and this car is driving like in a forward direction. Okay, so it's moving along the z-axis. All right, the angle, this theta for our components, I'm going to draw our components right here. So this is f and y. And this right here is our f and x. Okay, our theta will be right there. That will be our theta. All right, And at this point, let's define our fnx and our fny's using our sines and cosines. So fnx is opposite of this angle, so we can state that fnx is equal to fn sine of theta, and we can say fny is adjacent to this angle, so it'll be fn cosine of theta. All right. What I'm going to do here is I'm going to show you, I'm going to move this fnx so that it is along this axis right here, just so that I can explain what's going on. So this is my fnx. Right? I just moved this top vector down a little bit. So what this fnx is doing is it's pushing the object towards the middle of the circle. And the reason why that's important is because we want all of our centripetal forces to be along this axis, along this x-axis. And so the only force that is along the x-axis, according to our free body diagram, is this fnx. Okay, it points towards the middle of the track. So if we were to come up with a centripetal force equation, we would say that the centripetal force is equal to mass times the centripetal acceleration, which is equal to fnx. And remember, this is positive fnx because it's pointing towards the middle of the circle, once again represented with this dot. If it was pointing away from the circle, it will be negative. But for us here, it is positive. Now, if I were to substitute in my formulas, we can see that it'll be the mass of the car times the tangential velocity squared, all divided by the radius, is equal to fn sine theta, because we defined fnx appear to be fn sine theta. Right? So that is our base equation. Now before we move any further, I have this fn here. I want to define that. And I'm going to define that using my net force y equation. And the reason for that is because we have this f of g along this y-axis, and this f of g is equal to fny. Now the cool thing about this, and this is a neat little mathematical trick, is we know that along the y-axis, this object is in equilibrium, meaning that this car isn't being lifted off of the floor and it's not being driven into the floor. And so we can say fny minus f of g is all equal to 0. Our net force is 0. And it's because there is no acceleration along that axis. So I'm going to just clean it up a little bit in my next line down. I can now replace my stuff with formulas. We said fny was fn cosine of theta, and we said fg was mg. And so we can say that mg is equal to fn cosine of theta. So if we want to define what normal force is, we can say normal force is equal to the weight divided by the cosine of theta. Okay, so I'm going to highlight that because we will need that in a little bit. Okay, our normal force is equal to mg cosine of theta. Now, I want to make a quick little side detour to show you the difference between a regular inclined plane problem versus this banked curve problem. Right? So here, if we have mg and we have f of n, right? And this is a regular inclined plane problem where the object is sliding up and down the ramp. And we said that this was mg, so this is our theta. This would be cosine of theta, and this would be mg sine theta. Okay. If I were to define what normal force is according to our adjusted axis, and once again, this whole idea of the adjusted axis comes in. Remember, this object is accelerating, or it's the motion of this object is along this x-axis. Okay, this adjusted x-axis, and that's why we adjust it like so. All right. So if I were to come up with the equation for normal force, we can take a look at it as Fy is equal to My, which is equal to Fn minus mg cosine of theta. We know it's not accelerating in the y direction, so 0 is equal to Fn minus mg cosine of theta. And we can say that f of n is equal to mg cosine of theta. Now this is really, really cool. So if the object is moving around in a circle, the weight is being divided by cosine of theta. But if the object is not moving around in a circle, but just allowed to slide up and down the ramp, it is being multiplied to cosine of theta. Okay, so to give you what this means for us in the real world, let's come up with let's use a calculator to see what the numbers turn out to be. So let's say our weight of the object, let's just make it easy for us, and we'll say m times g just gives us 1. So 1 divided by, and let's just say the angle is 30. Okay, so if the weight is 1, okay, and we divide 1 divided by cosine of 30, that means the normal force will be 1.15. So that means that the floor is pushing up more than the weight. And we can say that because the weight is 1, right? Mg is 1 divided by cosine of theta, and that means the normal force is 1.15. So the floor is pushing up, okay, more than the actual weight of the object. However, if we multiply the weight, which is m times g, so 1 times cosine of 30, and once again, just coming up with these numbers, the banked curve is 30 degrees. That means the normal force is less than the weight. So that means the floor isn't pushing up as much on the object as its actual weight. So I'm going to write that down because that is very important to know. When you're moving around in a circle, okay, the way that the formula comes out is that the floor pushes on the object, that is more than actual weight. All right. And over here, we can say floor pushes on object that is less than actual weight. And so here we come across a very cool little concept where normal force is your apparent weight, and your mg is your actual weight. So f of n is apparent weight, so that's how apparently heavy you feel. I don't think I spelled apparent right. And what that means is, let's say you're sitting in a chair and someone pushes on your shoulders down. Okay, that means the surface will push back on you more, and so you feel heavier. All right, so in this case, when you're moving around a circle, your body will feel heavier, or the object will feel heavier because the floor is pushing up against it more compared to if it wasn't moving in a circle and it was just sliding down. Cool little tidbit. All right, back to the original problem. So here we have mv squared divided by r is equal to f of n sine theta, and we just found what f of n is equal to. So what I'm going to do is I'm going to substitute in this fn into this original equation. So we get mv squared divided by r is equal to mg cosine of theta times sine of theta. All right. Now, if you are a trig whiz, then you'll see that we have sine theta divided by cosine theta, and that simply gives us tangent of theta. So mv squared divided by r is equal to mg tangent of theta. All right. So also, if you are a algebra whiz, we see that we have m here on the left-hand side and m on the right-hand side, and so we can simply cancel those two out. It divides out evenly. So we get v squared over r is equal to g tangent of theta. And if I were to ask you, what is the velocity that this car needs to travel in order to stay a certain radius away? Okay, we could rearrange this equation to have the velocity be rg tan theta, square root of it, right? Now from there, if I were to ask you like different things, you can find theta, you can find the radius. There's a lot of different ways that you can manipulate this one equation based on your problem and your scenario. All right, so that's how you solve, and that's how you set up a banked problem or a object on a banked surface. A lot of really cool things happening here. Now, if you want to experience this right here in real life, here's a really cool experiment that you can do. If you get a balloon, right, and you put a penny in a balloon. So let's say we have a balloon here, and if you put a penny in a balloon, okay, it could be a penny, it could be a dime. I think nickels work the best because they don't have that rough surface, that rough edge. But you could get that coin. It could, if you spin the balloon around and around and around, the coin will be against the surface as it rotates around in a circle. Now, if you stop spinning it and you let the force of gravity take hold, okay, the object will slow down. And when the object slows down, you'll notice that it slides down down the curve. But if you speed it up again, the object will move up the bank. Okay. So that's a cool little way of seeing this action just happen in real life. All right, I'll see you next time. Bye-bye.